Okay, hi there, my name is Darren, and within this hopefully quick tutorial, I'm going to be taking you through the idiosyncrasies of setting up a hygrothermal model. Now, to do that, I'm going to have to run through a couple of bits. There's going to be a section about verification of the solver behind the model. So we'll jump into that straight away. Let's go there now. So that's a quick one. When you're building out a solver, you build out the solver for hygrothermal modeling to the best of your ability, and then you fine-tune it, you tweak it. And when you tweak it based on methods that have been around for some time now, and I'm going to point to two specific methods here. The Hamstead method. This is the first method that we tested against, and it was hyper useful from a calculation point of view because it allowed us to go ahead and do tests against benchmark 1, 2, 3, 4, and 5, with specific reference to 4, which was the trickiest one to undertake a multi-layered response as a result of driving rain. But you're free to get into these. We're not going to go into the details now because it could take all day to talk about the idiosyncrasies of effectively what these tests provide. But for yourself, that is test number 1. Second test is the EN 15026. Now, should you be snooping around and looking at tests, you're going to find this one quicker than you find Hamstead, because this EN 15026 has been used in Delphin, it's been used in Woofy, and guess what? Our results are exactly the same as the stated test results from the aforementioned software. Effectively, you get points across 7 days, 30 days, and 365 days, and your solver is set up or just simply verified to meet those points. So we can see the points on the red line here, on the orange line, and on the blue line for 365, 30, and 7. The only reason I'm going into a bit more information here is that I personally think that this one here is probably the one that's required, or both could be required from a top-down perspective, from a ABCB perspective in Australia, or from a governing perspective elsewhere in the world, because we need to have some level of verification to solvers, or you'll have people pulling these things up left, right, and center. Anyway, that being said, this is all useful stuff. If you ever want to get into effectively what's under the hood, this is your best chance to do it. So all available for you. And of course, down here, deep in the depths of the workflow, moisture, you will find a very, very useful Q&A. So you might want to get into, I don't know, I can't see my keyboard, OSB, for example. There you go, the master OSB. You may want to get into, I don't know, driving rain or something like that. Completely up to yourself, but there is a lot of Q&As there, and this area is just going to build out more and more. But I believe we probably, pull together about 60 questions there that you can search through. And then finally, you have the input side of things all available for you should you want to look up definitions, because I won't be jumping into those definitions here. What I will be jumping into very quickly, though, is the application itself. So in this model here, you can see it's set up for Hobart, Australia. We've got a kind of a high mass system. We've actually got a mix. We've got a high density, high porosity system here on the outside being solid concrete, and then we've got an air cavity, and what we call in Australia at least is a class 4 vapour-permeable membrane. That is it has low vapor resistance for the rest of the world, and you can convert it into your own terminology. Then you have some insulation as a steel stud. Of course, on the platform, you can go ahead and get rid of steel studs. I don't really think anyone should be adopting steel studs like this, so I'm going to go ahead and nuke that one because I'm not a fan. Let's make it official. And then what I'm going to do, I'm just going to change up a couple of things here. This isn't required. for anything other than just improving this process. Let's go ahead and take that out. So I just remove the installation altogether there, and I'll add that back in. Ignore me for a second. I'm off on a tangent. There you go. I'm finished. So, okay. So we have a wall system that's been built out, and we have other tutorials that enable you to get into that. We're going to slightly ventilate this wall system, not because solid concrete is typically slightly ventilated, because it's typically face sealed, but to show a few features in the Hygrothermal sim, I'm going to leave that there. And what I might do is I might build it out a little bit further there. 20 mil, why not 35 mil? We're going to resolve the conductivity and the revised materiality as a function of that depth there, so you don't have to worry about that stuff. And then down here, if you want to jump into Imperial, which I honestly don't fully understand, metric is also there. So feel free to do both. Effectively, you change that, you change your inputs, you change your outputs. They all convert to Imperial if that's the way you want to go. Finally, site. Should you want to go ahead and bring in your own climate file, you can go ahead and do that here. So that's not an issue at all. You just click configure, upload an EPW from your local machine. EPWs, WAC files and EPWs can be interchanged and converted, and we will also allow WAC files pretty soon as well. It's not our biggest priority, but we will get onto that one and enable that. So you'll just see effectively that will expand to select an EPW or WAC file. Done deal. So once you've done that, if you want to do that, go ahead and do that. And the useful bit about doing this is that you can then go ahead and interrogate your climate file, make sure that it has the data that you expect it to have for a hygrothermal study. And I'm talking about particularly about precipitation data here. If it has no rain within the data file, it's pretty useless from a hygrothermal point of view. So well worth doing that, because even data with assumed to come from reputable sources, we still see data points missing or data points much lower than what you would expect. And it's important for you to contextualize as you do these studies. Now, speaking of studies, let's go ahead and move on to this one. So we got a mixed mass wall system here. We're going to assign a study to it. Okay, so I'm going to stick with the subject of mold growth here. And should you want to add in something else, we surely can. Relative humidity, temperature. Actually, let's do that. We're going to have to add more information over here. Elsewhere, we've got common inputs for the internal conditions. Sorry, the initial conditions. In reality, you don't need to touch this. We're going to detect whether you're northern hemisphere, southern hemisphere, and you typically start at the start of winter. If you want to customize it, go ahead, go for your life. But you start it at the beginning of winter as per conventions, and then on the initial temperature, you can leave that at 20 degrees Celsius or the equivalent in Fahrenheit. Nothing to touch. You have equilibrium moisture content, which I'll come back to that in a second. We have cavity assumptions. We have the definition of the grid across the hygrothermal simulation itself. We have driving rain, external and internal surfaces, external and internal conditions, and reporting. So we're going to get into all of those independently, but let's first set up the scope. So I've matured the scope to be mold growth, relative humidity, and temperature. What that means is that I expect to see outcomes for all of these things. You can push this out to 10 years. Let's go ahead and do that. No harm. We're going to leave this on the south orientation because we're in Hobart, Australia. So the non-equatorial facing side of the building is being used because it has the least drying capacity. That's most likely to be true. If you don't believe it, you can go ahead and hit create. Go ahead and bring in your file through here and check out what orientation has the least drying capacity. So just telling you that feature is there, and it's available in other tutorials. Now, coming back to this now, I'm going to re-edit it just so you know. You can export and import these as JSON files, useful for you, so you can store it locally, but also useful for us because you might want to store it locally and then send that file to us should you have any questions. And then it makes life so much easier to support you. So our objectives are in, our run periods in, our orientations in, inclination, leaving it at 90 degrees. And then from a floor area perspective, I'm just going to lock it down as a small residential home of 270 meter cubed. Done deal. Moving on to mold growth. So when you go ahead and select a scope, you have to apply effectively a recipe to a rule set to that scope. And this particular scope for mold growth has a bunch of options to determine exactly what you want to do. So this is all this is doing is being hyper opinionated about what your study is. So in this case here, we haven't selected a study on the entire construction itself, or a study on the material index, which is the position of the material in the wall, or a study on materials with so-called sensitivity as a function of mold growth, and you'd need to jump into DA07 to understand that in more detail, or the external and internal. We've decided that the material type is what we want to look at, and that's insulation. Now, if you want to optimize the sensitivities around the insulation, you can. So if I said it was medium resistant and it had a glass wool mean decline coefficient of 0.2, which is all as per DA07 in Australia, or ASHRAE 160, get into that yourself. We can override it there. So we only want to see these in our results. We want to set a maximum value. Again, DA07 specific information. A maximum value of 3 is set here, and we can set it to wherever we want, whether we want all cells within the actual insulation itself, a minimum depth into the material, or max for the external depth. A bit confusing, that one. External cell of material. I'm going to select the external cell of the material, right? And I'm going to update that for a second because I'm just going to explain there. The cold point in this system is likely to be adjacent to the point with the highest vapor resistance. And even though this is a pliable building membrane, a vapour-permeable membrane with relatively low vapor resistance, it's still going to be much higher than everything else around it. So this is where you'd expect condensate to form on the interface between it and a glass wall. So that's the reason why I'm setting up my study for mold growth there. And you may actually want to expand that out and also look at the backside of this solid concrete here. So this interior facing surface of solid concrete, that may also be a point that you would want to look at, specifically if you're trying to meet the National Construction Code requirements, which would require all of these surfaces to be reviewed. Now, as we go on, we've got a maximum value of 3, external cell of the material. It's for all hours, and there's a few things there. You can shift the start week of the study, etc., but we're not going to do that. And if you want to customize things, let's go ahead and customize them. We can call this, I don't know, let's just call this glass wool mold growth index. There you go. Okay, just for the want of a better definition there. So I've saved that. I didn't mean to come out of it. And we go there and we can see glass wool MGI. Okay. What I'm going to do, just for simplicity's sake, I'm going to address the same. I'm going to add the same setup for each one here, just so it's easier. So I'm going to do this again. Glass wool RH, done. Okay, and if you can't spell wool like me, that's how you fix this. So there you go, and I'm going to copy that now and bring that in because I'm going to do exactly the same for temperature. So all I've done is repeated the study, and I'm going to say minimum temperature here for the insulation, and I'm only going to be interested in the outer side of that insulation, which is selected here. I'm going to customize that again, be lazy, call that temp, and I've set that up for a minimum temperature of 10. So, okay, that's that. I keep coming out of that. I shouldn't do that. So we have our maximum mold growth of 3. We have our relative humidity max of 80%. And we have a minimum value of 10 for the temperature. Not important why this is set at 10. It's related to an estimated dew point risk, but I'm just showing this so we can see that in our results, which you'll see very soon. Now, next up, initial conditions. As mentioned, just start at winter, initial 20 degrees, 70 degrees Fahrenheit, that's fine. You don't have to worry about that. Next up, you can select your equilibrium moisture content. You can select other initial moisture methods if you want, but equilibrium moisture content is a standardized way to do it, and 80 or 90%. Again, this is DA07 stuff. So if you want to meet DA07 or ASHRAE 160, you'll need to dig into this. It has a multiplier on that value. So effectively, we take the moisture storage content of the moisture storage curve at 80% and double it. Or you take it at 90% and double it. Now, there are rules within ASHRAE 160 DA07 that determines that materials, effectively wet materials poured on site, i.e. concrete, must adopt a scenario of 90% times 2. You might find that problematic, but we have it set up there as well, should it be applicable to the study. Okay. That's a very specific setup, and I'll get into that in a specific course. Next up, cavity ventilation. So we've done quite a lot of interesting work on cavity ventilation, and one of the challenges in hygrothermal simulations is the simplicity of cavities, because hygrothermal simulations are effectively set up as solid material assessments, not air assessments. So they have effectively simplifications for cavities. So you'll find that these are quite sensitive. What we're finding is that it's more useful to talk about dynamic cavities, and a dynamic cavity effectively uses ASHRAE fundamentals to determine the air change rate within the cavity as a function of some inputs around the effective openness of perpend openings in your brick systems, etc., in order to establish what an air change rate is. Now, you will see over time that this list begins to grow more, and we've got a much more detailed, established finite element process being built out at the moment that will effectively boost our level of confidence around what this is, how you can take advantage, or how you can better understand your climate-based cavity ventilation method rather than pulling a number out of the air. And this is effectively what a lot of us have had to do for a long time, because there is no academic agreement about what cavity ventilation should be, because it's such a diverse thing. So I'm going to leave this on here. It doesn't matter what the inputs are, but effectively just saying that there is an opening. That opening has a opening effectiveness, and it's differentiated by its height, and it has a emissivity of 0.9 in the cavity itself. And effectively, this opening then enables a air velocity to be introduced into the 35 mil cavity that we have adopted in this study, and then we'll use the wind speed and wind direction in order to effectively nominate a dynamic air change rate. Interesting stuff, a lot to talk about. Grids, we'll jump over this nice and quick. You can set up your grid scheme, the cell count, or if you want to go detailed, and you can override the details here. I wouldn't suggest that you ever need to touch this outside of academia. Moving on, driving rain. At the moment, you can add water sources. If I add source here, I'm going to add a water source as rain, and I'm going to say, hey, I want to set that up to the external material. Actually, it's all set up there. That's all you need to do. External cell of the material, rain fraction, 1%. This is again DA07 ASHRAE 160 stuff, and set it up for free water saturation. And that's all you need to do for driving rain. We then have rain exposure factors, deposition factors, and adhering fraction of rain. We'll be providing a slight tweak to these inputs very, very soon, which will mean that you can effectively set drop downs in order to set these values, as opposed to nominating a value through a slider, which will make it far easier for you to understand. Effectively, the rain exposure is a factor based on the severity of the exposure and the height of the building. Deposition factor is, I forget the exact definition of the deposition factor. Yeah, it's more to do with the again about the deposition of the precipitation down the face of the wall. So effectively, the deposition factor itself, the larger the number, the more precipitation runoff will be received to the wall, and then the final value here is the rain adhering fraction, so that's how much is sucked into the wall at that point in time. So in other words, choose that, and it means that you've got rain running down your wall. Go back down here somewhere, and you'll find yourself being set up for a wall that is pretty well protected below a steep sloped roof. That's that. Next up, again, a lot of stuff here that you don't need to necessarily touch. I would argue that in most cases you won't have to touch this at all. In the particular example that I've got here, there is a useful application for it, and I'll just go through it quickly. So in terms of the convection method, you can leave that at 10. That's set up for a wall system. Vapor method, you can leave it as wind driven. All fixed, it's up to yourself, but it doesn't actually vary that much in reality. For the coating method, should you have a coating on the exterior side of the porous construction, which is the concrete in this case, you can go ahead and select a SD value, which effectively means that you are overriding the adhering fraction of rain, which was mentioned previously. So over here now, we don't actually need this in play, because effectively that this here is overriding that anyway. So we'll probably do some automation there. Solar absorptivity, we're talking about colors of walls here. Long wave emissivity, don't need to touch that. 0.9 is a standard. Ground emissivity, again, you shouldn't really need to touch this at all. And effectively, the difference between ground emissivity and reflectivity is they are a whole. So if that's 0.9, that's 0.1. And then the cloud method, just to talk on it for a second, if you don't have any cloud data within your EPW, within your climate file, then 0.66 will be determined as atypical. If you do, then we'll just adopt what's in the climate file. Internal surfaces, again, not much to do here. Not much to do at all. You can adopt a convention there. I think that now has been updated to a value of 8. So just to be clear, this is just a couple of days old, this front end, but we're well worth getting into. And then the SD value, again, you could go ahead and pop on some paint or something like that. And that's all you need to do. So you popped on paint on both sides. This is on the plasterboard, this side. This is on the outside of the concrete, and keep going. External conditions, should you want to change your climate file and make it more onerous, you can. So effectively what this does is that it bumps up the relative humidity in the EPW by the percentage that's adopted on this slider. That's all it does, but it does have a meaningful impact on your outcomes. And I personally have a strong preference for this, because what it means is that it's a far simpler way to ensure that effectively the average of the last 10 years or the extreme of the last 10 years are included in your study. So it's not exactly as prescribed by DA07 or ASHRAE 160 in terms of the climate methods methodology. However, it is a good method if you want to bump up the moisture. So I'm going to bump up the moisture like that. And then on the internal condition side of things, we have the greatest hits here from ASHRAE 160 down to sine curves with 13788 and 15026 in between. I'm not going to cover these. I'm just going to default these because we've selected a very small home back here, 100 meters squared. I'm going to say, well, actually, do you know what? I'm just going to pop that up there. I'm going to pull these around a little bit. Let's say this is more a 3-bedroom apartment or something like that. So we're going to do a south wall and a 3-bedroom apartment, and then I'm going to just bump up the number of bedrooms there. And then you get the automatic determination of the moisture load that's going to get dropped into the model as a result. Now, when we are modeling this here, you can leave these as defaults. You can probably put on heating and cooling if that's applicable to you. But besides from that, that's all for another day. And then when it comes to the reports, we enable you to get a lot of reports, probably too much at this point in time. But I'm going to run all of these now for us so we can see how this works. And just to repeat, you can export this file. I would suggest that you do export the file, and you typically do not need to run or save results anymore because the simulations are fast enough to run within a few minutes in most cases, and should negate the need to use credits in any way to store information on our servers for you to retrieve later. So in other words, effectively you can just rerun this anytime you want, and it will make no difference to you. I'm going to hit run one simulation and wait for the results to come back. Okay, so I wasn't astute enough to make a reference to how long that took, but that was probably 90 seconds or so. So that's 90 seconds or so for a calculation to determine the glass wool mold growth index. Ooh, that's a bit high. We can see why it's high, because we've got high relative humidity and we've got very low temperatures as well. So there's a combination of things here that we don't like for this particular system. Let's go ahead and view the details. So excuse me. So when you get your first summary of results, you will see the summation of all the studies under the summary. Okay, so you can zoom down here and see all that glorious information that provides a collative substantiation of your inputs. And there's a lot of it. So many folks may not want all of this stuff. You may find yourself copying and pasting and dropping into Claude or equivalent. That's completely up to yourselves, but there's a lot of data there for you. And really this gives you, that first point of call to go ahead and check your results. Now, I'll just talk about the inputs before I do get to the detailed results. Elsewhere on the input side of things, you can navigate through to your materials. Make sure you understand what's going on here. This is all important stuff. You can look at your cell distribution. Again, all important stuff. Probably less important here is you'll see a few tweaks and changes to this particular front end just to clean it up a little bit. And then we have all of those inputs there as well. So lots of stuff to look at to substantiate. And if you want to get into your climate in terms of external, internal temperatures, dew points, surface temperatures, relative humidity, external, internal, you see the internal relative humidity is very high because we've chosen a very small space. You can look at rain, its intensity, its flux, all very useful. Wind, from a direction perspective, from a speed perspective, and overall from an effective perspective, showing very limited effective wind over time. We can look at solar from a diffuse. Oh, that's looking a little bit low. Sorry, from a direct to a diffuse point of view. To reflected, so high reflection in this particular system, and irradiance, flux, heat, net, long wave, convection, absorbed solar, so lots of data. All of this is here really just to provide you with a full detailed substantiation of effectively what's in the climate file. So I'd probably argue that a lot of this would not be useful on a project by project basis, but it does allow you to interrogate data in a meaningful way. So it is worth having available. Now, once we've got through that, we're happy with everything, we can start to look at our results. So here we have the summary. And then over here for the glass wool MGI, then I have the details here. So effectively, the details here provide you with what your recipe was when you were undertaking the assessment. So I'm going to use the term recipe. Glass wool, we were interested in the mold growth index, and we were interested in the insulation of that mold growth index, or of the glass wool rather, in order to determine the mold growth index with a maximum value of 3. Okay, and we're going to look at effectively all hours for the external most cell in the material. So that's there, right? Just there. Okay, that's the external cell of the material. For relative humidity, same ding dong. We're going to look at that external, but we're going to set 80% as the magic number, and we can see excessive relative humidity in this system, which is fine. It is what it is. Glass wool. Let's go ahead and have a look at that. The temperatures get very, very low behind this concrete, which is not a surprise to me at all. But we've got the same recipe, insulation. Our value is 10 that we're targeting. We're going to do it for all hours. And effectively what we can see is failure across the board here. So not a great example if you're facing off against a client. Let's go into more details. When we navigate down on the mold growth, we can see that effectively we start low. And within the first year, we tap out. We get to the point where we've exceeded the value of 3 actually before the first year. So not a great result by any stretch of the imagination. And if you navigate down even further, you can see what effectively the statistics of this show us. It shows us that region 1, which is region 1, which happens to be cell 53 because it's only a surface cell on the outer side of the insulation, which happens to be 0.1 millimeters. That's our sample area, is only 0.1 millimeters. We have a distribution of 4.9, 2.8, 4.9, and 87.5% of time, whereby which mold growth is likely to occur, I should say. Okay, and then there's some statistical work on down here in terms of the start, the end, the min, max, probably more appropriate for other assessments. Moving to the RH, again we see the distribution at cell 53 for 0.1 millimeters, whereby which we can see a massive amount of moisture being built up there. And that is for good reason, because of the amount of moisture that is being collated in that cavity itself. For glass wool, we can see that we have a temperature profile here, and again that profile is pretty low. It's saying that, what's that? 30% of hours are below 10 degrees Celsius. So all meaningful, not what we want to see. We want to design this stuff out, which we can do. And then once we get through this process, you've taken these as your core results, then you get the opportunity to kind of interrogate the data in a bit more of a logical way. Not necessary this particular bit, but it does allow you to see your results, and you can navigate through temperature, relative humidity, water content, annual water content, and cavity. Now, what I guess the common threads of each is that you can look at a distribution of the start and end and the spread. In most cases, the flux, and the flux being the megajoule per megajoule divided by the meter squared rate, so the area adjusted value, and they are pretty useful. This area is going to see a little bit of tweaking here because there's a bit too much information from my perspective, but what I'll do here is I'll just go ahead and show you. So this is the start of your study. We start at 20 degrees because that's the initial temperature in the study. And then that drops down significantly as soon as we get to this cavity in the initial study, and then drops back up here. So effectively the temperature within the cavity is extremely low at the beginning of the study. And that could actually result in moisture risk, which is probably something that we will look into, because I don't believe that there is any determination from a methodology point of view, I don't believe there's any determination for specifying the actual temperature within a cavity. And what this would mean is you'd get condensate straight away because of how low the number gets. And then if we look at that now and juxtapose that to the end, what happens at the end? Well, the end of the study it remains low, but it peaks up towards the back, and that makes sense because that's the insulation doing its job. If we navigate to relative humidity, a similar story can be told, where we have high relative humidity at the beginning, and relative humidity declines throughout the study, and we get this point of, I guess, resistance on the back of the class 4 membrane in this particular case. So it tells the story, it tells the narrative there over time. Next up, we have water content, and there's a lot more to go through here because water content is defined in many units: kilograms per meter cubed, kilograms per meter squared, saturation percentage, and mass percentage. All of these are useful subject to what you're looking at. So if you're looking at the mass percentage from a concrete perspective, you'd expect that start to be down about 3%. It's not, it's much higher. The reason it's much higher is because the study was undertaken using the requirements of DAO7, the methodology that determines that we must multiply to extremely high levels from a moisture content perspective for equilibrium moisture content, meaning that this is set up to fail effectively as soon as you start the study, and it's a well-known issue in this particular space. Anyway, you can jump into many of these if you wanted to look at other subject matter such as plywoods or OSBs. You'd be interested in seeing what the distribution was here, and again you can see the spread over time and the flux there as well. Annual water content, should you want to see that, you can go ahead and see that and see how that changes over the years. All useful stuff to be able to tell a story, particularly to a main contractor that may not want to believe how risky systems are over time. And then finally, on the cavity side of things, so we display here an opportunity to interrogate cavity from a temperature and relative humidity perspective. So up the top we have climate, heat flux, moisture flux, and ventilation. All of this kind of combines to be your narrative around the cavity itself. So if I just look at the temperature and the relative humidity to start with, we can see that effectively we have low temperatures right at the beginning of the study and elevated RH. That is a recipe for high moisture, and for that moisture to then diffuse through the system, drying backwards and forwards in order to then effectively create challenges. We also have the graph up here which provides the temperature versus relative humidity. So as per this caption here, probably worth introducing these captions because they are everywhere. These are the hours that the cavity spent in each temperature and relative humidity band over the entirety of the run. Heat flux, again, useful. You can look at phase 1, phase 2. Okay, so you can look at the difference between impact on heating and cooling. Moisture flux, again, phase 1. Phase 2, you can see the impact on effectively that moisture flux, which is directly related to effectively pressure within on both sides of that system itself. And on the ventilation side of things, you can look at the difference between stack and wind effects. The ventilation ACH is your total. The ventilation wind is just for the wind, and you can see the stack. And what we can see down here is that the stack values here, and we've actually added on statistics for this now, but the stack values there represent low values. Your wind is more dynamic, and it changes from month to month and across the time of day, and will be still pretty low during the winter period. But we can see here that If we look at where we, I'm trying to grab the May to June, August there, that doesn't help me. But if we look at these values here, we can eyeball rough values of 5 or 6 or something like that as being an average. And that will be the value that will be impacting the actual simulation itself. Okay, I think that's mostly enough from the front end perspective. So what I've gone ahead and shown you is the high level stuff, the stuff that we post process for you to start the process of creating an opinion. The last bit I want to navigate to is this very important feature here, which is called results. So this is kind of detailed results. So probably could change that to detailed results or something like that. And all we're doing now is we're pulling up that design, pulling up that study, and giving you a blank slate to ask questions on it. So if we go to sensor here, we can go relative humidity, temperature, and water content at the moment. And we can say, okay, I want to understand something about maybe the cavity here. Okay, so let's say relative humidity. And let's say I wanted to go ahead and grab that term. I'm just showing you a way to do it. Oh, sorry, that was the last copy and paste that I had. Cavity, there it is there. So you can then select the cavity, and that has, as you can see on the top right hand corner, that's selected a line. So there, I'm going to select that cavity there, and then I'm just going to go all the way over to the other side of the cavity here, just to show the difference in relative humidity. Probably not the best example, to be quite honest, because it won't change a huge amount. But we can see that we have a direct risk of condensate due to the fact that relative humidity is at 100%, and vapor saturation is very, very likely to occur in peak winter. And on this face here, we have less of an issue. So that automatically tells me that while we have results pertaining to the insulation, there's going to be an impact here, because effectively you're going to get saturation on the back side of this concrete here or on the interior side. Now, let's go ahead and add another study on here. We'll go back here to our 18 and 46. So what I'm going to do, I'm going to delete that one there, 46, and then I'm going to go back to browse here, signals, sensor, temperature, and I'm going to find myself the cavity value for sorry, what was the cavity value? It was 18. What am I doing? Sorry about that, guys. So 18 here. So I'm going to go ahead and grab that 18. So I've now grabbed temperature, and what I'm aiming to do here is just overlay temperature and relative humidity here. It might take a bit of inference here. We can flick through the months should we want. And yeah, I'm just getting to the cold point here, but it actually looks like interestingly that the cavity itself, and if we go to graph signals here, I can just nominate along there, but the cavity itself maintains quite stable yet very, very low temperatures during those winter months, and thus increasing the risk of saturation on the back of the actual panel itself. So if we kind of broadly just zoom out here, and we can just scan over and look at 100% of relative humidity, which is just here, and we can see the temperature is very, very low. So there you go. That's an indication of why high mass concrete walls are not a great thing in cold climates, at least. That's all this video was intending to get you to. You can, of course, export your data, export it as a PDF. You can go ahead and send us questions should you want to. If you're watching this on YouTube, go ahead and follow along, because we are going to be making a lot more of these courses available on YouTube. So there you go. If you are on the platform, you have an account, this is your chance to go ahead and take the Q&A To be clear, the question and answers for the course help us to understand your level of knowledge. So these last 50 minutes or 45 minutes or so are there to both build your knowledge about how to use the platform, but also they're there to help us understand the relative effort that's been undertaken to use this tool. So when we see a Q&A that's been completed, the pass rate is low. It's 80%, and when I say it's low, it's relative to the how complex the questions are. So we don't make the questions super complex, but we do expect folks that are using this professionally to have passed that 80%. So it's a really good qualifier for us to ensure that you're on the way to becoming a competent, or are a competent person to use the tool, because your building surveyor or qualified professional is going to ask you at some point for some level of, proof that you have undertaken a study, and this could be part of that proof, because we provide a certificate of competency with each and every completed and passed course. So that's over to you. Go ahead, do it, jump into the course, pass it, publish it on LinkedIn. We'll let you go. Thanks a million for listening. Hopefully you found this a useful process and something that is going to help you in your professional career, or just even out of interest in the very interesting space of hygrothermal modelling. Thanks a million. Bye-bye.